All right, so let's look at the third FRQ right here. So I hope you have a periodic table in front of you because we're going to need it for the first one. It says write out the ground state electron configuration of the ion. So first thing, let's go ahead and write out the configuration for the atom. It doesn't matter if it's longhand or shorthand also. So iron, go all the way over, go up one. The noble gas you're at is argon. Then go back to the beginning of the period. It's 4s2, then 3d6. Now, this is for the ion though. So we have lost 2 electrons. So that means we're going to remove the outer electrons first. So we're going to remove 2 of the outermost electrons. So that would come from the 4s. So my ion configuration should be this. Argon 3d6. Common mistake, a lot of people will start removing electrons from that 3d, so you need to be very, very careful about where you're removing them. The electrons need to be removed from the outermost shell first. Alright, so the next question is asking you to compare the ionic radius. So anytime you are talking about periodic trends, and that could be the radius, that could be electronegativity, that could be ionization energy, you have to talk about 2 things. Okay, talk about the nuclear charge. So what's the magnitude of the nucleus, like the charge of it? So how many protons do you have essentially? And then also talk about the electrons. So the electrons, the closer they are to the nucleus, the more attractive they are. The higher the magnitude of charge of the nucleus, the more attractive they're going to be. And then also electrons repel each other. So if they're on the same energy level, or if electrons repel each other, so if you have electrons, more electrons, you have more electron-electron repulsions. All right, so let's look at this. We're comparing these 2 sizes. This one is smaller than this one. Well, they have the same number of protons, but the difference is this one has 1 more electron than this one. So the answer is the Fe+2 ion has more electron-electron repulsions. So if it has more electron-electron repulsions, the electrons are a little bit further away from the nucleus. They're not pulled in as tight. Okay. The next question, iron with +3 interact more strongly with water molecules. Give one reason for the stronger interaction and justify your answer using Coulomb's law. Okay, Coulomb's law essentially talks about 2 different things. It talks about 2 charged particles being attracted to each other. So the 2 things that impact that attraction will be the charge, so what's the magnitude of the charge, and then also how far apart they are from each other. So the closer they are, the more attracted they are to each other. The bigger the charge, the more attracted they are to each other. So iron with a +3, okay, well, there's 2 reasons that you could give. Okay, well, because this one's smaller, the water molecules can get closer, which makes it more attractive. The other reason is that the Fe with a +3, that has a higher charge. So the water molecules are going to be more attracted to that. So the magnitude of the charge is higher for the Fe with a +3, okay? And then also, this one's smaller, so it can get closer to the water molecules. Also, please don't get confused with nuclear charge and charge of the actual ion. What we're talking about here is the charge of the ion, not the charge of the nucleus. Okay, let's look at the next one. A student obtains a solution that contains an unknown concentration of Fe with +2. To determine the concentration of this, the student titrates with permanganate, okay? So we have essentially a redox titration. So this is one of the things that I want to point out. Really, you don't really even need to read this to do the next couple of questions. So I like to skip that, go to the question, then go back and refer to it if I need to. All right, the next part says, write a balanced equation for the half reaction of the oxidation of Fe from a +2 to a +3. All right. right? So it goes from this to this. Iron is balanced. There are no additional atoms, so I don't need to worry about adding oxygen or hydrogen. The only thing I need to do now is balance my charge by adding electrons to the more positive side. It needs to be brought down to, I've got a positive 3 on this side, positive 2, so I'm going to add an electron over here. Remember, you add the electrons to the more positive side to make them equal to each other. So a positive 3, negative 1 gives me a positive 2. That's all you have to do for that. The student titrates 10 milliliters of a sample. Calculate the value of the concentration if it takes 17.48 of this to reach the equivalence point. All right, it's a titration problem. So essentially you need to start with the item that has more information. That would be the potassium permanganate. So when you're looking at this, remember, this is the net ionic reaction. So the permanganate and the potassium permanganate, you're talking about the same thing. Okay? So start with the thing that you have more information about. You have a lot of information about the potassium permanganate. You only have a volume of the iron, so it's asking for the concentration. You need to get your moles of the iron. So we have 0.0174 8 liters. Go to moles. There are 0.035 moles for every 1 liter of the permanganate. And then you can go to moles of what you're interested in, which is the iron. All right, so moles on top of moles, look at your coefficients. You have 5 irons for every 1 of these. So then do the calculation. You're going to get 0.000612 moles, but that's not what it's asking for. Now you know how many moles there are. You need to do one more step and divide that by the volume of 10 milliliters. All right, that's going to give me 0.306 moles per liter. All right, next question. It's asking about lab equipment. All right, so the next question says, explain why the 25 milliliter volumetric flask would be a poor choice for delivering the required volume. So I would go back and read a little bit. It says, to deliver 10 milliliter sample of an iron solution in part E, the student has a choice of using a burette, a cylinder, a beaker, or a volumetric flask. So, a volumetric flask, if you remember, looks like this. Okay. So when you have a volumetric flask, you remember you fill to the line. So a volumetric flask only measures one volume. So maybe it's 10 milliliters, 100 milliliters, 500, but it says that it's going to measure 25. It really can only measure 25, that's it. So you can't just put in a certain amount and say, oh, I think that's about 10. That would be a very poor choice. So a burette would be the best choice, and then after that a graduated cylinder. We never use beakers to measure anything. We only use beakers as containers. Calculate the number of moles of the iron in the Fe2O3 that's produced. Okay, so essentially we took this mixture, we reacted it out, we created this. This is what we measured at the end, and we're trying to see how much iron created this. Well, okay, so the first thing, we have a mass of that. So we're going to take our mass of the iron oxide, go to moles. Well, how many moles is that? Okay, Okay, so 1 mole is equal to 159.7. So that gives me my moles of the iron oxide. Remember, this is for the iron oxide. Now, I need to figure out how many irons made that. How many moles of iron created that? So I'm going to go one more step and I'm going to go to iron. So if I know I have this many moles of iron oxide, well, for every one of these, I have 2 irons. And I'm just pulling that from the formula right there. Okay, so if I multiply that by 2, I will get 0.09431 moles of iron. So that's how many moles of iron that I get. All right, the next question says calculate the mass or the percent by mass of iron in the original mixture. Okay, so now what we're going to do is we're going to take what we did in part G. So you would get follow-through points for this too. So let's say that you calculated G incorrectly, but then you did H correctly with that number, you'd still get the point. So it's 9431 moles of iron. Go to grams. How many grams is that? Well, that's going to be 5 grams, roughly. Okay, so in this mixture right here, okay, there are 5.267 grams of iron. Well, take that and then divide that by the total. That gives you the percentage of iron in that. So, multiply that by 100 because it's asking for a percentage. You get 78.33. All right, so let's look at the next part. If the oxidation of iron in the original sample was incomplete, so that some of the 7.531 grams of the product was FeO instead of Fe2O3, would the calculated mass percent of the original sample be higher, lower, or the same or as the actual mass percent? So it's essentially asking you about a lab error. Okay, so the calculated mass percent of iron would be lower if this was true. A sample that contains FeO instead of Fe2O3 will have a higher actual mass percent of iron than a completely oxidized sample. So when the moles of the iron are calculated, assuming that the mass is all Fe2O3, the calculated number of moles of iron would lower the mass percent of the iron.